basically says force equals mass times acceleration. Now what that means is the force is proportional to the acceleration if the mass remains the same.
The second law is one of three laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move. So if you have an object with a mass that is accelerating, and accelerating means a change in velocity, that change in velocity is equal to the amount of force applied to the object. The way to say it with words is force is equal to mass times acceleration. The word velocity means a quickness in speed or motion.
So if you increase the force on something, it'll accelerate more rapidly. And acceleration is either speeding up, slowing down, or changing direction. So a rapid acceleration would be a change in speed very, very quickly. 10, 20, 30, 40, 50, 60, 70, 80, 90, really very, very rapidly. And the mass of the football, of course, stays the same. So to kick the football harder, it's going to accelerate more rapidly. Now what happens is this. The football only accelerates or speeds up as long as your foot is in contact with the football, applying the force.
The entire procedure unfolds in less than a second and a half, from snap to hold to kick. Most kickers take a three-step approach to the ball. The final step is the plant foot, which provides the stable platform for the kick. The kick itself involves the entire leg building the force necessary to launch the football. A kicker's foot is in contact with the ball for just 8/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball.
That's why you do the follow-through. As long as your foot remains in contact with the ball, applying a force, you can make that football speed up. The instant your foot breaks contact with the ball begins to slow down because gravity and air friction and such are going to begin to slow it down.
So when you kick a football, your foot applies force to the ball, sending it off at a high rate of speed, hopefully way, way down the field or through the goalposts. Cheering the field goal or Sir Isaac Newton? You decide. Sir Isaac Newton was an English physicist, mathematician, astronomer, natural philosopher, alchemist, and theologian, who's been considered by many to be the greatest and most influential scientist who ever lived. And speaking of influential scientists, let's go to the lab and see what Professor Phineas Omnibus is working on today.
And now, another How in the World brain game.
Welcome, explorers. I'm Professor Phineas Omnibus, and today we're going to demonstrate an endothermic process. What? In thermodynamics, the word endothermic describes a process or reaction that absorbs energy in the form of heat. Sounds cool, doesn't it? Here's what you will need for the old ice cube on a string experiment. Ice cubes, sea salt or kosher salt, string, glass and water. Let's get started. Fill the glass to the top with water. Place the ice cube in the glass. Cut your string about a foot long and get it wet. Place the wet string on top of the ice cube and let it sit for about a minute. Then pick up the string with one hand on each side of the string. Did it pick up the ice cube? Not really. So let's try something different. Put your string back on top of the ice cube. This time, get your sea salt or kosher salt and gently cover the string where it sits on top of the ice cube. Give it about 30 seconds to a minute. There we go. Using both hands, pick up the string again. The melting of ice is an endothermic process. Endothermic means that it takes heat from its surroundings, which causes temperature of the surroundings to decrease. When salt is sprinkled on the string on the ice cube, some of the ice melts. As it melts, it absorbs heat from its surroundings. which included the damp string. As the string loses heat, the water in the string freezes, causing it to attach to the ice cube. Astounding! Now, go grab some friends for this really cool experiment. Until the next time, I'm Professor Phineas Omnibus.
Well, that was certainly enlightening. What will he come up with next? Okay, that was downright annoying. But it does mean a great question.
How in the world does a hot air balloon work?
Man has been sailing along in hot air balloons since 1783. Over the years, these colorful objects have been used as military tools, advertisements, and just a great way to spend the morning. And in 200 years of ballooning, very little has changed. Why talk about it? Let's take a ride. For a topic this hot, the airship Curiosity is wasting no time heading for the hills. Located along the Rivanna River, Charlottesville, Virginia is nestled in the southwest mountains and is just east of the Blue Ridge and the Shenandoah Valley. Charlottesville is home to the University of Virginia, Monticello, the home of Thomas Jefferson, and quite a few hot air balloon enthusiasts. Crisp autumn mornings find the balloonist up with the sun, putting together the pieces for a morning flight.
Well, you have to get your basket assembled, lay it down, attach the balloon, then we use an inflation fan to cold pack or cold inflate the balloon.
Mandy Rafano has been a licensed hot air balloon pilot for 10 years. Once she and her crew get the basket in place and the balloon inflated, it's time to heat up the air inside using propane burners. How hot? How about 212 degrees or so? That's the temperature that water begins to boil. The burners continue to fill the balloon with heat until the ambient air is hot enough to lift it off the ground. Used as an adjective, the word ambient means surround, encircling. In the balloon's case, the surrounding air is heated up to cause lift. Hot air balloons slowly fill and then rise majestically in the early morning light. Colorful for sure, but did you know that there's basic science at work here? Yep, the ideal gas law and our old friend Archimedes and his famous principle. For example, the ideal gas law is a mathematical relationship between the volume pressure and temperature of a gas. For a given quantity of gas, the pressure P multiplied by the volume V divided by the temperature T remains a constant. Huh? That means when a gas like air is heated in a balloon, its volume will increase. So, the volume increases, it fills the balloon, soon it's full and flows out the hole at the bottom. Hot air contains fewer molecules and will be less dense than cooler air. Remember our old friend Archimedes? When we learned about how a boat floats, Archimedes told us that when an object is suspended in a fluid, the buoyant force acting on an object is equal to the weight of the fluid displaced. So if an object is less dense than the fluid, it floats. Although hot air balloons can come in many shapes and sizes, they all have three essential parts: the burner, which heats the air, the balloon envelope, which holds the air, and the basket, which carries the passengers.
Is that horizon up there? How's it doing on the surface there?
So, what's missing from this picture? How about a steering wheel or a rudder?
We actually can steer the balloons depending on the varying winds of the day. If the winds allow us, we can almost steer them like an airplane just by finding different layers to ride out.
Skilled pilots can read the air, so to speak, and maneuver the balloon horizontally by changing the vertical direction. To move in a particular direction, a pilot ascends and descends to the appropriate level and rides with the wind. Since wind speed generally increases as you get higher in the atmosphere, pilots can also control horizontal speed by changing altitude.
We may find due south at 1,000 feet and east down on the surface and maybe west up high.
A pilot heats the air with the burners to make the balloon rise. To descend, there are two methods.
Either let the balloon start to cool off, it'll initiate a slower descent, or this particular balloon that you flew in had one large deflation vent called the parachute valve. We'll give a good pull on the red line for about 3 seconds, and that'll vent a large amount of air out and initiate a much faster descent.
And eventually that descent leads to a landing, where a balloon chaser helps bring it to the ground. After all,
Ballooning definitely has its ups and downs.
And did you know that in order